So am I audible? So Sasi Kumar, Banu Prakash, Gokul, do you have any doubts? You guys able to
No,
see me?
sir.
So I assume you guys are able to see my screen also, right?
Yes, sir. Yes, sir.
Okay. So this week, third week, we will be studying how to solve linear differential equations and their applications in solving the linear circuits, linear RLC circuits. So can you guys tell me where in an RLC circuit does a differential equation come? Why does that differential equation come? So can anyone tell me why are the differential equations in circuits? So if we will consider for an inductor, okay, we know an inductor is given like this, okay, and this is the current to the inductor as well as the voltage across the inductor is denoted like this. So the relation between the voltage across the inductor and the current flowing through it is VL with respect to time is L into DIL by dt. Okay, so like because the inductor is an energy storing element, the the voltage and the current are functions of some previous values. So because of this, there arises differential equations when we when we solve these RLC circuits. Okay, so now we will have the introduction. Like over here, there are when we write the differential equations using KVL, KCL, or something like mesh analysis or nodal analysis, which we have done, we will get the circuit in terms of differential equations. So one method to solve these differential equations is to use Laplace transform, and that is a method which will convert it into frequency domain, and it is very useful method. It is makes solving very easy. But for right now, in this week, we will try to solve it using linear differential equations only, so that we can get understanding about how the solution of inductor current or the voltage varies with time. Okay. Yeah. So in like the as I told that the inductor and capacitor are there in a network and they store energy. Okay. So because they are storing energy, that is why there is what you say. Those differential equations are formed in the circuit. And so now we will try using the classical method for solving differential equations. So now we want to try to do the old-fashioned method as well as we want to learn how to do it quickly. So let us consider this. Suppose there is a circuit like this. Okay, there's an inductor, there's a resistor, and there is a voltage source. Okay, voltage. So can you tell what will be the KVL equation? Suppose this is the current. So what will be the KVL? When we apply KVL, what will be the differential equation which is formed? So Gokul or Banu Prakash or Shiva, Saiti.
Sir, yes, sir. Yes, sir.
What will be the
Sir,
differential equation?
R into I of t plus L into di by dt is equal to V of t.
Okay, so we get V of t is equal to R into I of t plus L into di of dt. Okay, so what is the order of the differential equation?
Order 1, sir. First order differential equation.
Okay, and how many energy storing elements are there in this circuit?
1, sir. Inductor.
So because there is only a single energy storing element, the order of the differential equation is 1. Okay. Now, let us assume there are two inductors in parallel. There's a resistor and there's another voltage source. So, this is L1, this is L2. Okay. And this is a current I. So what will be the order of this when we apply KVL to this mesh? What will be the order of the differential equation?
2, sir.
Order will be 2. Okay. So in this case, what actually happens is this inductor L1 and L2, we can represent it by a single inductor, L equivalent. So effectively, these two inductors, which are two separate energy storing elements, can be combined into a single energy storing element. That is why when we apply KVL to this mesh, we will get a differential equation which is of only order 1, even though there are two energy storing elements. Okay. So now also let's consider if there's an inductor, if there's a capacitor, if there's a resistor. So what will be the what do you say, the differential equation here?
Into R into 1
Sorry.
by C integral I of t equal to V of t.
Okay. No. Could you repeat? V of t is equal to R into I of
R
t.
into I of t
Huh?
plus 1 by C
Huh?
integral
Huh?
I of
Okay.
dt
Huh?
plus L into di by dt.
L into di by dt. Okay. Okay. So this is the differential equation form. So this is of what is the order of the differential equation?
Two, sir.
2. So actually this is an integral differential equation. It has an integral term as a differential term. So we will again apply differentiation. So when we again differentiate it with respect to time, it will come L d2I upon dt2 plus R into di of dt plus 1 by C into I of t is equal to d of dt of V of t. Okay. So this is a thing. And also this integration term is there. So it is from suppose t equal to 0 to some time t. So that time we will have to add an initial condition of the capacitor voltage. Okay. So the voltage across the capacitor, when we apply KVL here, Vc of t will be equal to 1 by C integration from time t equal to t0 to time t, I of which varies with respect to t into dt plus the initial voltage across the capacitor. So any doubt in this?
No, sir.
Okay. Oh. This is the thing. Okay, so now we will consider how to solve linear differential equations. Okay, so we will consider this circuit where, like this, let us assume this circuit. This is the circuit L, R, V of t. Okay, the previous circuit. So we apply KVL as before, and we got V of t is equal to L di of dt plus R into I of t. Okay, so this is a first order linear differential equations. Huh? So now we want to solve this differential equation. So how will we write it as? We will write it as di of dt plus L upon plus no sorry R upon L into I of t equal to V of t upon L. Till this, is it clear? Banu Prakash, Siva, Saiti, any doubts?
Yes, sir. Yes, sir.
Banu Prakash, I
No,
can't hear
sir.
you.
No, sir. No, sir.
Yeah, clear, sir.
Okay. So now go to the next page. So when there is a method to solve linear differential equations of the first order, okay, and that is as follows. If it is like dy upon dt plus p into y is equal to q. If it is a first order linear differential equation which is of this form, dy upon dt plus py is equal to q. Okay, where p and q are either they are constants or they are only functions of x, or they are only functions of x. That is, p can be written in terms of constants or and x, and q can be written in terms of constant or x. Okay, in this case it is time, x is time, sorry. Okay, f into t. So what do we do in such a case? We There is something known as an integrating factor, I into f. Okay, that is known as an integrating factor. That will be equal to e raised to integration of p into dt. Okay, this is the integrating factor which we will use. And what will happen is the solution which we will get when we solve this linear differential equation, first order linear differential equation will be of this form. Y into the integrating factor is equal to integration of q into integrating factor into dt plus some constant k. Okay, some constant k. So we will apply this method for solving this previous equation. Okay, over here p is equal to r upon l, so it is a constant. It is not dependent on current, it is only dependent on r upon l, which are constants. Okay, and q is equal to v of t upon l. Okay, this again we can write like this. So now we will write integrating factor is equal to e raised to integration of p into dt, e raised to integration of r by l into dt. So it will be e raised to r t upon l. Okay, so we get it of this form. Now we will solve. So it will be y. So here y is the dependent variable, and in our equation the dependent variable is I, current. So we will get it of this form, I into e raised to r t upon L is equal to integration of Q. Q is what? It is this voltage V of t upon L into e raised to r t upon L into dt plus k. Okay. So this is the equation which we have found. Now we will assume this V of t to be a constant value. Okay, V of t to be some DC voltage. If it is a DC voltage, we will write V of t is equal to V of Vs, V supply. Hmm? So we will get it of this form. I into e raised to r t upon L is equal to integration of V supply upon L into e raised to r t upon L into dt plus k. Okay. So when we integrate this, we will get I into e raised to r t upon L is equal to Vs upon L into L by R into e raised to r t upon L plus k. Any doubts in this?
No, sir.
So we get it of this form. We divide throughout by e raised to rt upon L. So here it will become 1, here it will become 1, and here it will be e raised to minus rt upon L. So we get it as Vs upon R plus k into e raised to minus rt upon L. Hmm? Now what do we do is, we know that initially in this circuit that we assume that the current through the inductor is 0. Okay, so we'll assume that the current through the inductor is 0. So, okay. Let us assume that this is the current through the inductor. Huh? We will assume it to have some initial value I of 0. I of 0 is the current through the inductor at time t equal to 0. Let it be I of 0. Okay. So, what we'll get is, we will, so in this equation we will put t equal to 0. If we put t equal to 0, what will we get is, Shiva, you have any doubt?
No, sir.
Okay. So we will put t equal to 0. So we will get it to be I of 0 is equal to Vs upon R plus K. See, e raised to minus 0 is 1. Okay. So it will be plus K. So we get K to be equal to I of 0 minus Vs upon R. Hmm? Now, if we will consider this circuit, the final value of the current, that the current which will flow through the circuit at steady state will be equal to Vs upon R, because the inductor acts as a short circuit. Okay. So in steady state, the current through this circuit through the inductor will be Vs upon R. That is the final value of current. So that we write it as, that's why we write I of, that's why we write Vs upon R is equal to I of infinity. Okay. So now we will write I of t is equal to Vs upon R, which is I of infinity, plus k. K we will write it to be I of 0 minus I of infinity into e raised to minus RT upon L. Okay. So this is the equation which we have got, and we know, and we also can write it as I of t is equal to I of infinity plus I of 0 minus I of infinity into e raised to minus t upon tau, where tau is equal to L upon R, and it is known as the time constant of this circuit. Okay. Tau is equal to L upon R, which is the time constant. So So, Siva Saiti, can you tell what is the dimension of tau? With Banu Prakash or Gokul of 46, do you know what is the dimension of tau? Tau is what dimension? Okay. So tau, seconds. Yes, yes. So tau has a unit of time. Okay, tau has a unit is time, or seconds or minutes or whatever. Okay, in seconds only. Okay, so this is how, this is the thing. This is the time constant of the circuit. So in this method, we will solve linear differential equations of the first order. Okay, there's this standard method which is used, and this method is very useful to solve first order linear differential equations in circuits. And these first order linear differential equations you will get in circuits where there is, like a resistor and an inductor, or in circuits where there's a resistor plus capacitor. Okay, so in these sort of circuits, when there's a resistor and a single energy storing element, which could be either an inductor or it could be either a capacitor, then we will get first order linear differential equations. And to solve it, we will use this method. Okay, so this is the current through the inductor, which can be like in a shortcut. If we want to have a shortcut, we don't want to write the entire differential equation of the circuit, and then we will find, if we don't want to do that, we can just directly use this method. This method states that the current through the inductor, the function of current through the inductor with time, is the current through the inductor, the final condition, plus the initial condition minus the final condition into e raised to minus t upon tau. Okay, so this is one easy method which can be used to solve this what do you say, first order linear differential equations, like it's a shortcut formula. Another way is, and similarly for RC circuit, let us go, let's consider our RC circuit. Okay, it can be R, this can be C. Okay, this can be voltage supply, like that. So the voltage across this capacitor, okay, initially let the voltage be 0. Vc of 0 is like the initial voltage across the capacitor. Okay, so in case they say that, assume that the capacitor is uncharged or discharged, then the initial voltage will be 0. Okay, but if they don't say that, if they say that the capacitor is charged to some value 5 volt or something, then the initial voltage across the capacitor is 5 volt. So that you must keep in mind. So when we will solve the differential equation, okay, there'll be like some sort of switch and it will be closed at time t equal to 0. So when we solve the voltage across the capacitor as a function of time, we will get it as Vc of t will be equal to Vc of infinity plus Vc of 0 minus Vc of infinity into e raised to minus t upon Rc. Okay. So this is applicable for circuits where there's only a resistor and a capacitor. And what do we say? This time constant is tau, which is equal to Rc, and this also has time units of seconds or time. Okay, so this is for RC circuit. RC circuit. So Banu Prakash or anyone else, any doubts? So now, okay. So now we will solve this equation, this question. Okay. Okay, so this is the question. There is a DC voltage source, there's an inductor, there's a resistor like this. Then there's a switch, and there's one more resistor connected over here. So at time t equal to 0, this switch is closed. Okay. And now we want to find the expression for current through this resistor of 12 ohm and the current through this resistor of 8 ohm. So we will proceed. So Gokul, what will be the initial current through the inductor? Initial current through the inductor, what will be the value?
Sir, in steady state inductor act as a short circuit, sir.
So
So
before
current I
time,
is equal to 20 by 12, sir. It is 1.607 amps, sir.
okay. 1 minute. Okay. 20 by 12. Okay. So let us consider IL of 0. Okay, that is equal to 20 volt upon 12. So it is 5 by 3. That is equal to 1.66 ampere. Okay. That is the initial current through the inductor. So that's why the initial steady state value of the inductor current was 0. Of at time t equal to 0 was 1.66 ampere flowing to the inductor. Now, at time t equal to 0, the switch is closed and this resistor 8 ohm comes into the circuit. So after t greater than or equal to 0, we will write the circuit in this form. It will be 4 Henry over here, 20 volt here, and there will be some resistor R effective. Okay. This R effective, what will be the value of this resistor be?
$4.8, sir.
Okay. That is a parallel combination of this 12 ohm resistor and this 8 ohm resistor. So it will be 12 into 8 divided by 12 plus 8. That will be equal to 12 into 8 divided by 20. Okay, that is 4.8 ohm. Okay. So now we will apply KVL to this circuit. Okay. When we apply KVL, we will get 20 minus 4 di upon dt minus I into R effective is equal to 0. This is the current through the inductor. Okay. So it will be so you will get it to be of this form. 20 minus 4 di by dt minus 4.8 I is equal to 0. Therefore, 4 di by dt plus 4.8 I is equal to 20. Okay. We will further simplify di upon dt plus 1.2 I is equal to 5. Any doubt till here?
No, sir.
Okay. So now we will now solve it using that integrating factor method. Okay. This is P and this is Q. Q is equal to 5, P is equal to 1.2. So the integrating factor, we will get it to be e raised to integration of P into dt. Okay. That will be e raised to integration of 1.2 into dt. That is equal to e raised to 1.2 into t. So the solution will be I of t into e raised to 1.2 t is equal to integration of 5, okay, into e raised to 1.2 t plus some factor k. okay, into dt. Any doubts in this?
No, sir.
So we will get it to be of the form. Now phi is a constant, and integration of e raised to ax or something, e raised to at, will be equal to e raised to at divided by a. Okay, so we will get it to be of this form. I of t into e raised to 1.2 t is equal to phi divided by 1.2 into e raised to 1.2 t plus k. So psi t, you have any doubt?
No, sir.
Okay. So we get it to be of this form. I of t is equal to phi divided by 1.2 plus k into e raised to minus 1.2 t. Okay. So this is the value of I of t. Now, what do we want to do is we have the initial condition of I at time t equal to 0. We know I of 0 was equal to phi upon 3. Okay, that we had already established. So what do? We substitute t equal to 0. Okay, we put t equal to 0 in the circuit. So we get phi upon 3 is equal to phi upon 1.2 plus k. Okay, so we get it to be of the form phi into 1.3 minus 1 upon
Sir,
1.2. Yeah,
how 5 upon 3 comes, sir?
we solved no? Initial current 20 upon 12 is equal to 5 upon 3.
Okay, sir. Okay, sir. Okay, sir.
So we get it to be of this form 5 into 1.2 minus 3 upon 3 into 1.2 is equal to k. K is 5 into minus 1.8 upon 3 into 1.2. So what will this value be? Can someone solve and tell me?
Minus 2.5, sir.
So we get k to be equal to minus 2.5. Okay. So now the equation will be equal to, okay, what is 5 divided by 1.2?
4.16.
So it will be 4.1667 minus 2.5 into e to the power minus 1.2 t. Okay, this is the equation of current through the inductor. Okay, so this is what we have got. But what is the question asking? They want us to find the current through this resistor of 12 ohm and the current through this resistor of 8 ohm. Okay, so how do we get it? So what are your suggestions? How to find the current I1t and I2t? So Banu Prakash, any suggestions? Okay, Siva Saiti, you were saying something?
No, sir.
No, sir. No one has any suggestions how to proceed. Okay, so there's a current division rule. Okay, so what did we get is, this is our original circuit. So we have found the equation for this IL of t. Now we want to find the current through I1t and I2t. At time t equal to 0, this switch is closed. So this current will get divided over here and here. So it will get divided in this form. The current through the 12 ohm resistor will be equal to 8 upon 12 plus 8 into I of t. Okay. That is 8 of the other resistor divided by 12 plus 8. That is the current through this one, through this resistor of 12 ohm. So that would mean it will be equal to 2 upon 5 into I of t, which is therefore I1 of t will be what? Will be 0.4 into 4.1667 minus 2.5 into e to the power minus 1.2 t. So what is 0.4 into 4.1667? Bhanu Prakash, Gokul.
1.668, sir.
Okay. So that will be equal to 1.667 minus 0.4 to 2.5 is 1. So equal to e raised to minus 1.2 t. Okay. We have found the equation for I1 of t. Okay. So actually this meeting will close in 2 minutes. In around 2 minutes it will close. Then I'll again start this meeting so I can rejoin because I do not have premium version of Zoom. So that's why there's a limit of only 40 minutes for the meeting. Okay. So till then we will solve. So also the current to the second resistor will be I2 of t, which is equal to 12 divided by 8 plus 12 into I of t. That is equal to 3 upon 5 into I of t, or equal to 0.6 into I of t. So I2 of t will be equal to 0.6 into 4.1667 minus 2.5 into e to the power minus 1.2 t. Okay. So what is 0.6 into 4.1667?
Two 2.5, sir.
Okay. That's equal to 2.5. And what is 0.6 into 2.5?
1.5, sir.
Okay, so it'll be 1.5 into e to the power minus 1.2 t. Okay, so thus we have found the equations for I1 of t and I2 of t. Okay. So now we will go back to the question. So they have told us to determine this constants A1, B1 as well as K1, and again the constants A2, B2 and K2. So you guys are able to hear me, right? Okay, is my screen visible?
Yes, sir. Yes, sir.
So now we have to find I1 of t in terms of A1, B1 and K1. So I1 of t is equal to A1 plus B1 into, so it will be, we have I1 of t is equal to A1 plus B1 into e to the power minus K1 into T. Okay. So here A1 will be 1.667, B1 will be equal to minus 1, and K1 will be equal to 1.2. So any doubts in that?
No, sir.
Okay. So what do we get is A1 1.667, B1 is a minus 1, K1 is this. Similarly, for I2T, it is A2 plus B2 into e to the power minus K2T. Okay. So A2 will be equal to 2.5, B2 will be equal to minus 1.5, and K2 will be equal to 1.2. Okay. That is how we just there. Now we will proceed to the next question. Okay. Alright. Okay. So this is the circuit over here. Okay. So there it consists of a resistor, two capacitors which are there, and there's a switch. The switch is closed when t equal to 0. So initially the current was only flowing to this capacitor. When the switch is closed, current will flow to this capacitor as well as to this capacitor as well. Okay. Now uh, they say the capacitor on the right side was uncharged. Huh? And what will be the voltage across the capacitor, across this capacitor in steady state?
Open circuit in steady state capacitor and this open circuit.
Hmm. It will act as an open circuit, but what will be the voltage across it? See, so initially, if we assume, if we look at the circuit, it is actually like this. This is 8 ohm resistor. This is this capacitor of 10 millifarad. Okay, this switch was open, so this part of the circuit does not come into the picture. So when you say open circuit, it means this current which is flowing over here was 0. Okay, the current was 0. So for the current to be 0, so the current, let us assume the voltage over here is VC. Okay, so current will be equal to 5 voltage at this side minus voltage at this side minus VC upon 8. That will be the current to the resistor because it has to satisfy KVL. Okay, but because at steady state capacitor acts as an open circuit, what does that mean? That is VC will be equal to 5 volt. Because when VC is, because we know at steady state the current is 0. So for the current to be 0, the voltage across that capacitor should be equal to 5 volt. Okay. So has this cleared your doubt? Any doubts in this?
No, sir.
Okay. So initially the voltage across this 10 millifarad capacitor was 5 volt, and the voltage across the 8 millifarad capacitor was 0 volt, because they say the capacitor on the right hand side was uncharged. Okay. Hmm. Now what is the charge stored on capacitor on this 10 milli? What is the formula for charge stored in the capacitor? There's an equation for charge.
Q is equal to C into V, sir.
Okay, stored in capacitor. Q is equal to C into V. Okay. So now there's charge stored in the left hand side capacitor that is equal to 10 millifarad into 10 to the power minus 3 into 5. Okay. That is equal to 50 millicoulomb. Similarly, the charge stored in the second capacitor will be equal to 8 into 10 to the power minus 3 into 0. Okay, that is 0. So the total charge stored in both the capacitors at time t equal to 0 is Q equal to Q1 plus Q2, which is equal to 50 millicoulomb. Okay. So, any doubts in this?
No, sir.
Okay. Now, when we close the switch t equal to 0, the effective initial voltage. Okay, what will be the effective initial voltage across both the capacitors? See, when you close the switch at time t equal to 0, both the capacitors are in parallel. So the voltage across both the capacitors must be equal. But before closing the switch, the voltage across one capacitor was 5 volt and the voltage across the other capacitor was 0 volt. So after closing the switch, immediately the voltage will settle to some value. Okay, and we want to know what will be that value of voltage. Okay, so that is our goal, to find out what will be the value of voltage. So how we will do that is, there will be some effective initial voltage. Okay, there's something known as effective initial voltage. The effective initial voltage across both the capacitor. Okay, so that is what we want, the effective initial voltage across both the capacitors. Now we know for a capacitor, the voltage across the capacitor will be equal to Q upon C. Okay, so Q we have found to be 50 millicoulomb divided by C effective. So the effective capacitance is equal to this two capacitors connected in parallel. So when we connect two capacitors in parallel, what will be the effective capacitance?
C1 plus C2.
C1 plus C2. So it will be equal to 10 plus 8, which is equal to 18 millifarad. Okay. So now the effective initial voltage Vc of 0 is equal to Q upon C effective, that is equal to 50 divided by 18. Okay, 15 to 10 to the power minus 3, 18 into 10 to the power minus 3. So 50 divided by 18 is how much?
2.777, sir.
Okay, it is 2.77 volt. Okay, so this we have established. Now, as I said, okay. Now this circuit in steady state, it will be of this form. Five will be 5 volt, 8 ohm resistor over here, and 18 millifarad capacitance. Okay, this is the effective circuit in the final steady state condition. Okay, so we want to find this voltage Vc of t. So can you tell me what will be the final voltage, steady state voltage across this capacitor? That is Vc of infinity. What will its value be? Any idea? So in steady state, the capacitor acts as what?
Open circuit.
Okay. For it to be open circuit, what should be the voltage across the capacitor?
Sir, 5, sir.
Yeah. So VC of infinity will be equal to 5 volt. Okay. Now the voltage across the capacitor with respect to time, as we have told, there's the simple formula, that is VC of infinity plus VC of 0 minus VC of infinity into e to the power minus t upon RC. Okay, RC is the time constant. So VC of t is equal to 5 plus 2.777 minus 5 into e to the power minus t upon RC. Okay, that will be equal to VC of t will be equal to 5. What is this 2.77 minus 5? Will be this 5 minus 2.223 into e to the power minus t upon RC. So what is t upon RC? So what is 8 into 18 into 10 to the power minus 3?
0.144.
Okay. What is 1 upon 0.142?
7, sir.
Oh, 7. Okay. Actually, when I've done the calculations, I've got it to be 5 minus 2.223 e to the power minus 6.94 t. Okay. Oh, almost 7. So this is the voltage across the capacitor, and it can be expressed as AB plus BV into e to the power minus t upon tau. Okay. So AB in our case is equal to 5. BV in our case is equal to minus 2.223. Okay. And T upon tau is 0.14 something, 104 something. Okay. So any doubts in this?
No, sir.
Okay. Now we have to find the current. Okay, the current I of t. So how do you think we will find the current I of t? This is equal to I of t. So can you tell what will be the equation of current I of t?
Sir, KVL apply.
Yes, apply KVL. So we will get it to be of this form. KVL, right? So V of t. So that will be 5 minus I of t into the resistor, that is 8, minus the capacitor voltage VC of t equal to 0. So I of t is equal to 5 minus VC of t upon 8. Okay. So we get I of t to be equal to 5 minus 2.223 e to the power minus 6.94 t upon 8. The whole upon 8. Okay. So that's why we get I of t equal to 2.223 divided by 8 into e to the power minus 6.94 t. So we get I of t to be equal to, what is the value? 0.27785 e to the power minus 6.94 t. So this is the equation of I of t. Any doubts in this?
No, sir.
Okay. So now these are the expressions of the voltage and the current. Okay. Now let us draw it in how actually it looks. If we go, okay, like this. Okay, this is the voltage V of t. It will be like this. So time t equal to 0. Okay, this is time. The voltage will be equal to 2.77 volt, and it will increase like this in this rate, and finally it will settle at 5 volt. Okay, so this is the graph for the voltage across the capacitor with respect to time. As we have told initially, the voltage at Vc of 0 will be equal to 2.77 volt, and at final value is 5 volt. So this is how the graph will look. Okay, this is how the graph will look for the voltage across the capacitor. So the capacitor voltage will start charged to something, and then as time varies, it will reach this final value. Okay. Now, the time that it will take to reach this final value will be like approximately pi into tau, pi into time constant. That approximately that is the amount of time by which the capacitor voltage will reach almost 5 volt. Okay. That is some approximation which is used, which is some empirical way we have. Similarly, the current to the current to the resistor with respect to time, I of t will be changed like this. It will be equal to 0.27785, and it will decrease. Okay, it will decrease like this, and at steady state its value will be 0. Okay, so this is the curve which is given at 0.27785 into e to the power minus 6.94 t. So any doubts in this?
No, sir.
Okay, so these are the graphs of the capacitor voltage and the inductor current. So inductor current has an exponential decay, and capacitor voltage has 1 minus e raised to something. So it comes in this form. Okay. So this is how we have got the capacitor voltage and current equation. Yeah. So we got AI to be equal to 0. Okay. And we got BI to be 0.27785. And we got tau. Tau to be equal to some 144 millisecond. Okay, so it satisfies this. Similarly, Vc of t is 5 minus 2.223. So AB we get to be 5, and BB we get to be 2 minus of 2.223. So it comes within this range. So our answer which we got is correct. Okay. So now we have solved equations where it was a first order linear differential equations. We were there, and in those circuits we have solved and we have found the solution, and so we are confident how to proceed when it comes to first order differential equations. Now we have to consider for second order differential equations. Okay. So if you will observe over here, okay, this is second order differential equation, and we will write it in this form. Okay. d2y upon dt2. This y can be the capacitor voltage or it could be inductor current, anything. Okay. Plus a into dy upon dt plus by is equal to x of t. So x of t is like a forcing function, like the function which is driving the circuit. Okay, this function which is driving the circuit is usually like the input voltage source or the input current source or something like that, something similar. Okay, that is what is driving the circuit. So when we will solve the equation, we will get it to be of this form. Y of t is y of n of t plus y of f of t. So n of t is the natural response when this driving function, okay, when this driving function is equal to 0. When this driving function is equal to 0, then yn of t will be the natural response of the circuit. And this natural response of the circuit happens only because there are, like, some initial conditions, like there's some initial voltage across the capacitor, or there was initially some current flowing through the inductor. Then there will be this natural response. Okay. Similarly, y f of t is the response due to the forcing function, and that is known as the particular integral or solution due to the forcing function. Okay. Then there's an operator d. Okay, d is an operator which basically does the differential with respect to time. This does differentiation with respect to time. So how they write this equation is d square plus ad plus b into y is equal to x of t. Okay. Now, okay. Now we can go to an nth order differential equation. Nth order differential equation means it has the power, or the highest differential is n. Okay. When there's an nth order differential equations, they will have some coefficients over here, a1, a2, dot, 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 an. And then when we write it in terms of this operator d, it will be written as d raised to n plus a1 into d raised to n minus 1 plus a2 into d raised to n minus 2 plus dot, 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 plus an into y. Okay, this is equal to x of t. So now we will find a characteristic equation. Okay. So what do we do is, suppose there's an nth order differential equation, we will write it in, suppose there's a third order differential equation, it will come as d cube plus a1 into d square plus a2 into d plus a3 into y is equal to x of t. Okay, so the characteristic polynomial or characteristic equation will be written as d cube plus a1 into d square plus a2 into d plus a3 will be equal to 0. So now when we will find the roots of the equation, we will get d to have some roots that will be equal to m1, m2 or m3. And so the natural response of the system will be given by a1 into e to the power m1t plus a2 into e to the power m2t plus a3 into e to the power m3 into t. Okay. So any doubts in this, Gokul?
Sir, what happened when M1 is equal to M2, sir?
So when m1 is equal to m2,
Roots are equal, sir.
it will be written as a1 plus a2 into t into e to the power m1 into t. Okay.
Okay, sir. Okay, sir.
That is when m1 is equal to m2. Okay. So this is the method, and like that. So they have told similarly when they are repeated roots, when the roots are distinct means the roots are different. When the roots are complex also, we will write it as like this. So it is this form. Okay. Now when we will solve, these are the things which we must keep in mind. So there are linear differential equations and boundary conditions will be given. So what are boundary conditions? Like it's the initial capacitor voltage, initial inductor current, or the initial change in the capacitor voltage, or the initial change in the inductor current. Those things also will be there. So when we will solve the example sum which is given, we will understand this. So first, what do? We write down the characteristic equation and we will solve for its roots. So we'll write down the characteristic equation and we will solve for its roots and we will get the roots. Now, if they are distinct, then we will write it in this form. If they are equal, then we will write it as this form. And if they are complex, also there is a form in which we can write it down. Then we will write down the expression for natural response, which will be the sum of several exponential terms, as we know. Then we will find a solution y of t, f of t due to the forcing function x of t. Okay, this will be a linear combination of the x of t and its higher order derivatives. Okay, we will look into this later. And then the total solution y of t will be the sum of yn of t and yf of t. Will be the total sum of the natural response plus the forced response of the system. Okay. Now, after we write it down, we will get their constants appear in y of t and xn of t, and they have to be determined. There are some constants which will come. Okay. like this A1, A2, A3. These are some constants. We don't know the value. They are just some constant values we got. So when we apply the boundary conditions, then it will help us to determine the values of A1, A2, and A3. Okay. So the like terms of, so we determine those constants from the boundary conditions. Okay. And then afterwards we write the total solution after applying the boundary conditions. So let us see this example one which they have shown over here. dy of dt plus 3y is equal to t. And the boundary condition is y of 0 is equal to 1. What does this y of 0 equal to 1 means? It means that at time t equal to 0, okay, y of 0 is equal to 1. Okay, that means the value of y at time t equal to 0 is 1. That is the boundary condition. So when we write, so this is the differential equation which we want to solve. So we will write it in terms of the operator d. It will come to be d plus 3 into y. Okay, this is equal to t. T is our forcing function that is equal to x of t. Now our characteristic equation will be equal to d plus 3 equal to 0. Okay, so we get d equal to minus 3. That's why we write natural response is yn of t is equal to a into e to the power minus 3t. Okay, now what they do is, this is the forcing function t. So forcing function is equal to the forcing function into some constant plus the derivative of the forcing function. So when we take the derivative of the forcing function, derivative of t, we will get it to be 1. So it is k naught t plus k1. And when we take further higher order derivatives, derivative of t is 1, derivative of 1 is 0. So that's why this will become 0. That's why we don't consider that. Okay. So what we get is total response of the system is equal to a into e to the power minus 3t plus k naught t plus k1. So Gokul, is this making any sense? Or it's getting too difficult? Um, just consider this and then we will start solving an actual sum and we will look into that. So we know that the forcing function will satisfy the differential equation. So we substitute the forcing function over here. And when we substitute it, we will get it to be of this form. K naught t plus k1 when we differentiate it with respect to time. We get it to be k0. Okay. Plus 3k0 to t plus 3k1 is equal to t. That is k0 plus 3k1 plus 3k0 t equal to t. Now when we take left hand side equal to right hand side, equating the coefficients, we get k0 plus 3k1 is equal to 0 and we get 3k0 equal to 1. That's why we get k0 equal to 1.3 and k1 equal to minus 1.3. So what do we get is k0 is 1 by 3, k1 equal to minus 1 by 9, and then we write it in terms of this. Okay. Now we want to find out a from the boundary condition y of 0 equal to 1. Okay. So we put t equal to 0. When we put t equal to 0, we get y of 0 is equal to a into e to the power minus 3t. So when you put t equal to 0, it becomes a. You put t equal to 0, 1 by 3 into 0 is 0, minus 1 by 9. So that's why we get a equal to 1 plus 1 by 9, that is equal to 10 upon 9. Okay. So this is how we find the constant a, and that's how we have solved this linear differential equation using this concept of forcing function as well as natural response of the system. Okay. Now, in our what we say in our circuits, most of the time the forcing function is either it is a sine function or it is a constant function. Constant means it is a DC, and the sine wave it is like it is AC supply. Okay, so those are the normal forcing functions which we will consider. Okay. So they have found using some method, they say that the forcing function, we will write it in terms of this. there's a characteristic polynomial of the second order differential equation. That is d square plus ad plus b. Okay, that is the characteristic polynomial of the differential equation, and this is the forcing function a into e to the power st. So if it was DC, if it was like a constant value, what do you mean by a constant DC voltage? Like suppose there's a DC voltage. Sorry, let us consider that there's a DC voltage. Okay, DC voltage. If there's a DC voltage, what it means? The like x of t, which is written over here as a into e to the power st, it means s equal to 0. That's why x of t is equal to a. Okay. So when it is like this, that is s equal to 0, what do we get is a into e to the power st divided by s square plus as plus b. So we substitute s equal to 0. When we substitute s equal to 0, we will get it to be equal to a upon b. Okay. Similarly, when it is a sine or cos, we substitute e raised to j omega t and e raised to minus j omega t and we solve it. Okay. So now we will try solving this equation. We will try solving the following differential equation. Okay. So uh, so this is this differential equation. Okay. Now what we will do, we will try to find the characteristic equation of this differential equation. So it is dy upon dt plus 2y equal to 10 cos 2t. So 10 cos 2t is the forcing function. So the characteristic equation is
Minus 2, sir.
d plus 2 equal to 0. So
Minus 2, sir.
yes, minus 2. So the natural response of the system will be equal to some a into e to the power minus 2t. Okay. So that we have established. Also, we have been given at time t equal to 0, the value of y is 0. Okay. So now we want to find the forcing function, the response of the system due to the forcing function. Now we have forcing function is given to be 10 into cos 2t. Okay. So cos 2t can be written in terms of 10 into e to the power 2jt plus e to the power minus 2jt upon 2. Okay. Which is equal to 5 into e to the power 2jt plus 5 into e to the power minus 2jt. Is this making sense? Or is there any doubt in this?
Sir, if sign coming means 2j was, sir.
If
In
it was,
denominator 2j.
yeah, in the denominator 2j will be there.
Okay, sir.
And this will become minus. Okay. So this is how we write the forcing function. Now they have told, okay, that the y f of t is equal to 1 upon d plus 2 into the forcing function. That is 5 into e to the power 2jt plus 5 into the power e to the power minus 2jt. Okay. It is of this form. So when we will take this differential term into this, what do we have to do? We have to substitute it. It will become like this. Okay. First I'll write simpler. Phi is a constant. We can take it out. It will be 1 upon d plus 2 into e to the power 2jt plus phi into 1 upon d plus 2 into power e to the power minus 2jt. Okay. So let us go to the next page. So y f of t is equal to phi. Instead of d, we will substitute 2j. Okay, it'll be 2j plus 2 into power e 2j plus phi into, instead of d, we will substitute minus 2j. So it'll become minus 2j plus 2 into e to the power minus 2j into t. Okay. So we will write it as phi, 2 we take to be common, it will be e to the power 2jt into 1 plus j plus phi into e to the power minus 2jt. No, this phi goes out into 1 minus j. Okay. Any doubts in this?
No, sir.
Okay, Lalita, you have any doubts? Okay. So what do? We multiply with a complex conjugate. So it'll be phi upon 2 into 1 minus j into e to the power 2jt. So this will be 1 plus j into 1 minus j plus e to the power minus 2jt into 1 plus j into 1 plus j into 1 minus j. So what will be 1 plus j into 1 minus j? If we expand it, 1 plus j into 1 minus j will be 2. Okay. So that will be equal to 5 upon 4 into 1 minus j e to the power 2jt plus e to the power minus 2jt into 1 plus j. Okay. So we will write it like this. This is equal to 5 upon 4 into e to the power 2jt plus e to the power minus 2jt plus j into, okay, we'll do minus j, sorry, minus j e to the power 2jt minus e to the power minus 2j into t. It comes like this. So now we know e to the power 2jt plus e to the power minus 2jt can be written as 5 by 4 into 2 into cos of 2t. And this e to the power 2jt minus e to the power minus 2jt can be written as minus j into
Sine
2j,
of it is sine.
2j into sine of 2t. Okay. So we will write it down as 5 upon 2 into cos 2t minus j, and j minus j square will be plus. So it will come to be 5 upon 2 into sine 2t. Okay. So this is the equation for the forcing function. Okay. Actually, this meeting will end, and then again I will again start it. Okay, because I don't have premium Zoom. So y of t will be equal to y n of t plus y f of t. That will be equal to a into power e to power minus 2t plus 2.5 into cos of 2t plus sine of 2t. They have given us y of 0 is equal to 0. They have given y of 0 equal to 0. We substitute it. So that means 0 equal to a plus 2.5. Because cos of 0 is 1, sine of 0 is 0. So that's why we get a to be equal to minus 2.5. So our final equation will be y of t equal to minus 2.5 into e to the power minus 2t plus 2.5 into cos 2t plus. Okay. So we have solved that equation. We have found it in terms of forcing function and the natural response of the system, and using the boundary condition, we were able to find the constant which was there in the equation, and we were able to get the final value. Now we will solve the sum, the last sum over here. Okay, this is our thing. So this is the circuit. The switch is closed at t equal to 0. Before that, the above circuit was in steady state. If it was in steady state, okay. So the capacitor was discharged. So if capacitor was discharged, the initial voltage across the capacitor at time t equal to 0 is 0. And the current, it was in steady state, okay. So the inductor was short circuit. So the current to the inductor will be how much? Before time t equal to 0, what is the current to the inductor?
600 by 60, sir.
600 by 60.
60 by 600, 0.1.
Sorry,
Yes.
sir. 60 by 600, sir.
So this is correct, okay. That is equal to 0.1 ampere. Okay. So that is the current to the inductor at time t equal to 0. Now we have to start solving this equation. So now at time after the switch is closed, we will apply KVL. Okay. Once the switch is closed, the circuit will become like this. 60, 220 Henry, 600 ohm, and 1 upon 6,600 farad. And this will be, and the voltage across the capacitor is V of t. So the voltage at this terminal also is V of t. Okay. Any doubts? The voltage at this point is equal to V of t because the resistor and capacitor are in parallel. So the voltage across both of them are same. So the voltage across the resistor at this terminal also is equal to the voltage across the capacitor, that is V of t. Okay. Now we will apply KVL. When we apply KVL, we will get 60 minus L di by dt, that is 220 di upon dt, minus V of t. Okay. That is the voltage across the capacitor. Any doubts in that?
No, sir.
That is what we applied, what we got by KVL. Now, when we apply KCL, okay, on applying KCL, we get I of t be equal to V of t upon 600 plus C into dV of t upon dt. This is the current through the resistor and this is the current through the capacitor. Okay, so thus we have two equations. So that's why I of t will be equal to V of t upon 600 plus 1 upon 6,600 into dV upon dt. Okay. Now, this is from here we will get V of t is equal to 60 minus 220 di of dt. So we will substitute over here. So what do we get is I of t. Okay, before that, what I'll do is I multiply by 6,600 throughout. So if I multiply this equation by 6,600, I will get 6,600 into I of t. 6,600 divided by 600 is equal to 11. That is 11 of V of t plus dV upon dt. Okay. Then from here we get v of t will be equal to 60 minus 220 di of dt. So we'll write 6600 I of t is equal to 11 into 60 minus 220 di upon dt plus d of dt into 60 minus 220 into di upon dt. Okay. Once we will solve it, it becomes 6600 I of t. 11 into 60 is equal to 660. 660 minus 220 into 11. That is 2420 di of dt. Now derivative of constant is 0. Okay. So this will be equal to minus 220 d2i upon dt2. So we will write this in this form: 220 into d2i upon dt2 plus 2420 di of dt plus 6600 I of t is equal to 660. When we divide throughout by 220, we will get it to be of this form: d2i upon dt2. 2420 divided by 220 is how much?
11, sir.
11 di of dt plus 30 into I of t is equal to 3. Okay. Now you find the characteristic equation of this. So that will be d square plus 11d plus 30 is equal to 0. Then we take the roots. We find d to be what?
Equal to minus 6 minus 5, sir.
Okay, minus 5 minus 6. Okay. So the natural response of the current will be equal to some a1 into e to the power minus 5 of t plus a2 into e to the power minus 6 of t. Okay. Now this is for the natural response. Now we want it for the forced response. So for the forced response, we know it is given like this: I f of t will be equal to 1 upon d square plus 11d plus 30 into 3. Okay. D we must substitute equal to 0 because it is a constant DC voltage. So we get it to be equal to 3 divided by 30. That is equal to 0.1. So the total response of the system I of t is equal to I of n of t plus I into f of t. That is equal to 0.1 plus a1 into e to the power minus 5t plus a2 into e to the power minus 6t. Okay. Any doubts in this?
No, sir.
Okay. Now the initial value of current, we know it to be at time t equal to 0, I of 0. What was the value of the current? We will see in the circuit I of 0, it was equal to 0.1 ampere. So I of 0 is equal to 0.1. When we substitute here, we will get 0.1 is equal to 0.1 plus A1 plus A2. Okay. That's why we get A1 plus A2 equal to 0 or A1 is equal to minus A2. Okay. So this is so then we get the simplified equation I of t is equal to 0.1 plus a1 into e to the power minus 5t minus e to the power minus 6t. Okay, because a2 is equal to minus a1. So we can write like this. Now we want to further solve this equation. We know 60 minus 220 di by dt minus v of t equal to 0. So we take that as 60 minus 220 di of dt minus v of t is equal to 0. So di of dt is equal to 6t minus v of t divided by 220. Okay. Now at time t equal to 0, di of dt at t equal to 0 will be equal to 6t minus v of 0 divided by 220. So what is the initial voltage v of 0? We have established that v of 0 was equal to 0. Okay. So that's why di of dt will be equal to 60 upon 220. Okay. 60 upon 220. 6 upon 22. Okay. Any doubts in this?
No, sir.
Now we know I of t is equal to 0.1 plus a1 into e to the power minus 5t minus e to the power minus 6t. When we differentiate it, we will get it as di of dt is equal to minus 5 into a1 e to the power minus 5t plus 6 into a1 into e to the power minus 6t. Okay, this is how we get it as. When we substitute t equal to 0, we will get it to be minus 5a1 plus 6a1 will be equal to 6 upon 22. So we get a1 to be equal to 6 upon 22. That is equal to 0.2727. This is a bit fast I did, but what I did is di of dt is equal to minus 5a1 e to the power minus 5t plus 6a1 into e to the power minus 6t. When I substitute t equal to 0, it will become minus 5a1 plus 6a1. That is equal to a1. Okay. Banu Prakash, any doubt? Okay. So we got a1, a2. So that's why we got the equation of I of t to be equal to point 1 plus 0.2727 e to the power minus 5t minus 0.2727 e to the power minus 6t. So any doubts in this?
No, sir.
Okay. So Gokul, you are from which college? From Andhra, right?
Animal Engineering College, Chennai. Chennai.
Oh, from Chennai. Okay, okay.
Chennai,
And
sir.
Banu Prakash?
Central University of Karnataka.
Sorry?
Central University of Karnataka.
Okay, okay. Yeah. Okay, so someone else just joined. Okay, fine. So now in the question, we were supposed to find the equation of the current as well as we were supposed to find the equation of voltage across the capacitors. So we found the equation of the current to be of this form: AI plus BI into e to the power minus 5t plus CI into e to the power minus 6t. AI we found it to be 0.1. BI we found it to be 0.2727. CI we found it to be minus 0.2727. Okay. So thus we have got those equations and those values. Now we want to find the voltage across the capacitor, the equation of that. Okay. So what do we do is we will go to this. Okay. This is this equation. This is the equation which we have 60 minus 220 di by dt minus v of t equal to 0. Okay. So from here we get v of t is equal to 60 minus 220 into di of dt. Any doubts in this?
No, sir.
Okay, so that we will write it as 60 minus 220 there into the, oh my, (220) into d of dt, current, the equation of current, that is 0.1 plus 0.27, 0.27 0.2727 e to the power minus 5t minus 0.2727 e to the power minus 6t. Okay. So when we differentiate, we will get it to be 6t minus 220. Derivative of 0.1 is 0. 0.2727 into e to the power minus 5t will be equal to minus 5 into 0.2727 e to the power minus 5t. Then minus of minus 6 into 0.2727 e to the power minus 6t. So when we completely expand it, we will get it to be of this form, to be 60 plus 30 e to the power minus 5t, no, plus 300 e to the power minus 5t minus 360 into e to the power minus 6t. So any doubts in this?
No, sir.
Okay. So thus we have solved it. We got AB, we have got BB, and we have got CB. Okay. AB we found it to be 60. Let us check. AB comes out to be 60. Okay. BB we found out to be 300. So we will check. It comes to be 300. CB we found to be minus 360. So it comes to be around minus 360. So what one thing to remember is they have a range. Okay, a range. So like suppose it was AB is coming 60. So any answer between 57 to 63 is valid. Okay. Like they are assuming like plus minus like 5% tolerance they are giving. 5% tolerance of 60 is 5 into 0.05, that is 3. So 60 plus or minus 3. In that any answer you give, it will consider that to be correct. Okay. So sometimes what happens is we have a problem that there's a decimal value. We got it to be 0.2727. So we don't know till what extent we have to take it, but they have given a range. That's why to consider those values. Okay. So that time you don't need to worry. Okay. So Deepak Kumar, you're from which college?
Sir, Prestige Institute of Engineering, Management and Research, Indore.
Indore, right?
Yes, sir.
Okay. Okay. You joined late today, actually.
Sir, because I forget it that today's meeting.
Oh. So do you have any doubts?
No, sir.
No, sir.
No, because
Okay.
I have done this assignment.
You have?
Sir, I have done this assignment.
Okay. Okay. You finished the assignment. Good. Congratulations. Okay.
Thank you, sir. Thank you.
So that's why today we have considered a lot of stuff. We have solved so many equations, everything. We have solved it only using linear differential equations. But when we go, suppose we do some Laplace transform or something, then solving these circuits will become much easier. That time we don't need to find, the differential equation. We don't need to write down. We don't need to be worried so much about the initial condition as well as what do you say, the type of forcing function, everything. All those, it gets integrated into the Laplace transform. When we consider Laplace transform, we take into consideration the initial condition, the forcing function, everything, and we get it into one particular format. And once we get it into that format, then we can solve these equations easily. So Laplace transform is a bit of a advanced topic, which you guys will learn soon. But right now we consider only the simple linear differential equations. So using these simple linear differential equations, we were able to solve it. So these linear differential equations, they will give you some insight into the circuit. Like when we consider this circuit, okay, in this, not this one, in this circuit, there's a voltage across the capacitor, the current as such. We drew the graphs of that. So we saw initially this was charged to 5 volt, okay. When we close this, and this was charged to 0 volt. When we close the switch, immediately due to charge balance, it has to balance the charge as well as maintain the voltages across the capacitors to be the same. So just at the instant when we close the switch, the charges in the capacitors will get redistributed, and the initial voltage at time t equal to 0, we calculated it to be 2.777 volt. Okay, that was the initial voltage across the capacitor. That was calculated to be 2.777 volt. Okay, now once it has been charged, it becomes 2.77 volt. Then the current will start flowing. Okay, current will start flowing. And when the current starts flowing, it will flow through this, and through this, it will charge both the capacitors to 5 volt. Okay. And so that we have drawn it in terms of this graph. Initially, the voltage was 2.77 at time t equals 0. And then it increases and finally attains 5 volt. And that takes approximately 5 into the time constant, 5 into the time constant. Okay, so that is one method which we use. That's why, the time constant has some significance. It helps us to determine how fast the circuit will reach the steady state value. So that is the case. Now we will consider some other situation. Okay, now we will consider some other situation where we consider that that this capacitor also was discharged. This capacitor also had voltage 0. It was uncharged. So that means the total initial voltage was 0. If that was the case, and also we also found that there's some shortcut formula which we can use, which we can apply for solving first order RC circuits or first order RL circuits. Okay. So Vc of t is equal to Vc of infinity plus Vc of 0 minus Vc of infinity into e to the power minus t upon RC. Okay. Now over here, the initial voltage was 2.77. Suppose the initial voltage was 0. Then we will get, what we will get is Vc of t is equal to 5 minus 5 into power e to the power minus t upon RC. So in such a case, what will happen is the graph also will be something similar. The graph will start at 0 because the voltage was 0. Okay. Initial voltage was 0. And it will rise like this. It will rise like this, and it will again settle around 5 volt. So the time it takes to settle around 5 volt will still be 5 into the time constant. Although even though the initial voltage of the capacitor was different, it will settle at around 5 volt at the final value in 5 into the time constant. Okay. So that is one of the significance of the time constant method. Okay, that's one of the significance of the time constant. So irrespective of the initial voltage across the capacitor, it takes around 5 into the time constant. That much time it takes for the capacitor to reach the final steady state value, irrespective of what was the initial capacitor voltage. Okay. Any doubts in this?
No, sir.
Deepak, kuch chamka?
What, sir?
You understood?
Yes, sir. Sir, I have a doubt.
Huh?
If like the capacitor was charged at 2 volt.
Okay.
then the final steady state voltage is 5 volt.
Hmm.
Then what is the time required for reach steady state of the
That time also
capacitor?
be fine to the time constant.
Okay.
That time also it will be from here, around here 2 volt it will start. It will go on increasing and it will come around here, somewhere around here. Okay, so all
will
this
take-
time will be fine to the time constant.
Okay, sir. It means any situation it will take 5 tau.
Yeah, 5 tau.
Okay, sir. Thank you.
Hmm. So that's why we like it's an approximation that if find the time constant, it will that much time it takes for the circuit to reach steady state. So that is a useful thing. One more thing to remember, keep in mind is it is e to the power minus t upon RC. RC is tau. It is a time constant. So the dimensions of time constant is in terms of seconds in time. Okay, that also you must remember. And yeah, so there was the concept of charge redistribution in the capacitors, which we considered in this sum. Similarly, we considered one differential equation with the forcing function, and we tried to understand how to find the response of the system due to the forcing function, which we did like this. So there's a differential operator D, okay, and the constant we can take it out. So phi into 1 upon d plus 2 into e to the power 2jt plus phi into 1 upon d plus 2 e to the power minus 2jt. So what we have to do in this case, instead of d, we have to substitute 2j. Okay, we substitute 2j instead of, and over here, instead of d, we have to substitute minus 2j. So we substituted those values, and then we multiplied by complex conjugates, other things. We did simplification, and we found it to be in this format. Okay, so what you must remember is any forcing function which we normally consider a forcing function which is there, x of t, it can be either a constant a, it can be either a constant a cos 2t, it could be either some b into sine of phi t, etc. All of that can be written in terms of a into e to the power s of t. Okay. For DC, it is s equal to 0. For here, a into cos of t, it is 2t, it is written as e to the power 2jt plus e to the power minus 2jt upon 2. Over here, it is written as b into e to the power 5jt minus e to the power minus 5jt upon 2j. Okay, this is how we write it. Then we write it in terms of this format, and then as they have told over here, okay, whatever is the forcing function which we write in terms of a into e to the power st, we substitute the value of s, we put d equal to s, and then we get the the response due to the forcing function. Okay, the forced response of the system. Okay, so this was one of the concepts which we studied. They have told sine omega t, we write it as e to the power j omega t minus e to the power minus j omega t upon 2j. Okay, similarly cos omega t we can write it in similar format. So x of t is the forcing function, and it is written like this. Because in normal electrical circuits we have either DC value, DC voltage source, or we have a AC voltage source. Okay, so it is either constant value A, or it is either written in terms of sine omega t and cos omega t. Then any doubts you guys have? Any other doubts?
Sir,
Yes.
how to score 70 plus mark in this subject, sir?
You have to just practice, that's all. Practice.
Okay, sir.
Yeah, like more you practice, more you go through some ceremony. Like, see what happens is usually we will read a concept, then we will solve an example sum, then we will go to next concept, solve next example sum, everything. But then what happens in the exam is one sum will come which will use what, which will you'll have to use multiple concepts. Then we will get stuck. Whether I have to use this concept or that concept, how to do it. So when we practice more and more sums, we will, we will use one concept, then we will use another concept. So when we use those concepts will get more reinforced into our mind. So we will know which concept we have to use where, all that. And also, the concept of silly mistakes. We make lots of silly mistakes. So, like 1 plus j, 1 minus j, something like this is there. Instead of plus, we do minus. And those silly mistakes are very hard to get rid of. So what they recommend is you must practice. As you practice, you will get rid of your silly mistakes. You will learn how to be more, you will learn methods how to verify your answer. You get an answer, then you learn how to verify whether this is correct or it is wrong, whether I've skipped something or whether I made some mistake like that. So that all those things you get only by practice. There's no alternative to that way. Mm. And you must remember the formulas also well. And also you must read the question properly. So now suppose I have this question. Okay, so I have this question. So I will first read the question, try to understand what it says. Then you find the initial conditions, you write down the initial condition will be like this. Then you see what it wants. In case you get this equation and like you have this, so okay, let's not assume this circuit, we'll consider this circuit, okay? In case the question was saying you have to just find V of t, okay? You didn't want us to form I of t. So what we did when where we were solving is, we had, where's it gone? We had this equation and we had this equation, okay? And in this equation, we substituted the value of V of t and found the differential equation in terms of d2i of d2t plus di by dt plus something like that. But instead, what we could have done is, this I of t value we could have substituted over here. Then we would have got the differential equation in terms of d2v upon dt2 plus some x in a into dv of dt plus some b into v of t equal to some other thing. And then we could have directly solved v of t. Okay. So those methods that you have to learn to carefully read the question, understand what you need, what the question wants, and how to solve it so that you can simplify it. Okay. Those are things which you must consider. Yeah. And be very, very careful while doing numerical calculations are a bit of a trouble. You can make some numerical error, everything. So be very careful consider the millifarad, microfarad, what it was. Millisecond they want to answer, or they want to answer in second. So that's why you must read the question very carefully. If you consider this question over here, tau, they want it in millisecond. Now, if you had not read it properly, you would have considered to be in second. So you'd have put it to be 0.140 something. But the answer is 140 milliseconds something. That's why, so you must see, sometimes in milliseconds, sometimes they want it in millivolt or something like that. So those things you must be careful. Okay. Then Deepak, you don't have any other doubts, anything?
No, sir. Sir, I want to crack the GATE exam. How it will possible?
So first you want to give GATE. You're in which year actually?
What?
You're in which year? First year, second year, third year, which year?
Sir, second.
Achha, second year. So you have time now. You can solve some MCQs you can solve. So even I started actually around after second year I started or something. Started solving
Yes.
MCQs for GATE. So one method you must use is like, what happens is we solve some sums. Okay, we solve some sums, and after solving the sum, we will We solve it, we understand it, and then we will forget it. We will go to the next topic and we will do. What a better way, so what you must do is you must again come and revise that topic. You must again come and revise, like you go through the syllabus, then you again come and redo that syllabus. So what will
Yes, sir.
happen is when you get one sum in the gate exam, you know that you have to use this method. You have to use this method to solve the sum. So that way it must be there. So like one method, like see, now you have solved these 3 questions, okay? So now you look back at this question. You do the how I will look back is there was this equation was there. It was a single first order differential equation. I found I found the inductor current I of t, and then I found that through the differential equation I solved the value of I of t, and then I did current division. I found I1 of t, I2 of t. Okay, so after solving the sum, you get a rough framework, like a rough step in your mind. Like I say if this sum came, first I do this, then I do this, then I do this, and then I do this. That way you must be very sure. You must be very sure that this sum comes, like this type of sum comes, means I have to solve this step, this step, this step, this step. That way,
Yes,
like
sir.
that. Then you must also know the the formulas. You must know very well. Like current division
Yes, sir.
means like this. I have to solve. This is the formula, everything, and you must also go through previous year's question papers. Okay, so when you go through previous year question papers, you get a rough idea like which topics they give more importance to. Like so which topics are more important. Like some network analysis is an important subject, so that you give more preference. Suppose you say like for another subject they don't give that much preference, so that you give less priority. Like that you do. The main thing is what you know, you must know it very well. Like that. Because no
Yes, sir.
one can complete the gate syllabus fully and completely and know everything. It is very hard. Only very few people are so exceptional. So like that is there.
Yes, sir. I understood.
Yeah. So just now you are only in second year only, na? So you can gradually you can just solve MCQs and do and keep solving. Not like I solved once and then I did solve for network analysis MCQs. Now I know any sum in network analysis I know. It won't work like that. You solve it once, you will afterwards you'll forget. Again you have to solve it. And then again you'll forget. Again you have to solve. Then you will know that ऐसा सम आया तो ऐसा ही करना है. That way.
Yes, sir. Yes.
Yeah.
Sir, have you cracked the gate exam or not?
Yeah.
You
I did.
cracked?
In 2020, I gave GATE and I qualified.
Oh,
Hmm.
congratulations, sir.
No, nothing that.
Because it is a very tough exam, I think, for engineering student.
No, it is not so difficult. Only people must study. That's all.
Yes, sir.
Yeah. Okay, so the meeting will end now. So hope we can. So next week also you will have same time for the syllabus. Okay, so all the best for getting what you want and work hard for it. Okay.
Thank you. Thank you.
Yeah. Okay.
Thank you, sir.
Okay.
Okay. Thank
Good
you.
night.
Okay. Good luck. Good night. All the best. Bye.